Out there, 2.5 million light-years away, something strange is stirring in the depths of the Andromeda galaxy, our closest galactic neighbor, and yet a place teeming with more secrets than we've even begun to unravel. Picture this, a vast, shimmering halo of ancient stars, dark matter, and something else, objects that defy explanation, lurking in the shadowy outskirts of Andromeda's sprawling edges. These aren't just stars or planets, they're cosmic anomalies, whispering clues about the galaxy's turbulent past and the unseen forces shaping our universe. Galactic halos are like the ghostly fingerprints of a galaxy's history, sparse, mysterious regions that stretch far beyond the bright spiral arms we're used to seeing. But Andromeda's halo is different. It's larger, more chaotic, and packed with strange formations that astronomers still struggle to understand. Some of these objects move in ways that shouldn't be possible. Others glow with unusual light, as if hiding secrets from another time. What are they? Where did they come from? And what do they tell us about the violent collisions, the lost dwarf galaxies, or even the dark matter that might be pulling the strings? This is a journey into the unknown, a dive into the cosmic wonders hidden in plain sight. Over the course of this video, we'll uncover 30 of the most baffling objects drifting through Andromeda's halo. Some might be remnants of ancient celestial battles, others could be hints of physics we haven't yet discovered. But one thing's for certain, each one has a story to tell, and together they paint a picture of a galaxy far more mysterious and far more alive than we ever imagined. So buckle up, we're about to venture into the depths of Andromeda's halo, where the ordinary ends and the extraordinary begins. Deep within the vast, ghostly halo of the Andromeda galaxy, something colossal hides in plain sight. A swirling behemoth of hydrogen gas so faint, so elusive that it barely registers on our telescopes. Stretching tens of thousands of light-years across, this nearly invisible cloud defies everything we thought we knew about how galaxies form and evolve. Hydrogen is the universe's most basic building block, but this cloud isn't just floating passively, it moves with a strange, almost purposeful rhythm, as if tugged by forces we can't yet see. Astronomers first detected it as a whisper in radio wave data, a faint ripple in the cosmic background noise, but the more they studied it, the more baffling it became. Most hydrogen clouds in galactic halos are small, fragmented leftovers from ancient star formation, but this one is monolithic, a floating relic that shouldn't exist at this scale. Some theories suggest it's the shredded remains of a dwarf galaxy torn apart by Andromeda's gravity, its stars long since scattered while its gas lingers like a phantom. Others argue it could be a rogue structure, a primordial fragment left over from the galaxy's violent birth, untouched for billions of years. Then there's the unsettling possibility that this cloud isn't just a relic, it's a harbinger. Simulations show that giant gas clouds like this could collide with Andromeda's main disk, triggering bursts of star formation or even feeding the supermassive black hole at its heart. If that happens, the galaxy we see today might look radically different in the distant future. But for now, the cloud drifts silently, a cosmic question mark hanging in the dark, one that challenges us to rethink how galaxies grow, evolve, and hide their deepest secrets in the emptiness between the stars. While the hydrogen cloud we just explored drifts like a silent giant, there's something far more unsettling lurking in Andromeda's halo, a clump of pure darkness. Not the absence of light, but the presence of something invisible, something that bends the very fabric of space around it. This isn't just any dark matter. It's a dense, unexplained knot of it, detected only because its gravity warps the light of distant galaxies behind it, like a cosmic magnifying glass turned upside down. Dark matter is already one of the universe's greatest mysteries, making up most of the mass in galaxies, yet refusing to interact with light or matter as we know it. But this clump is different. Most dark matter is thought to spread smoothly through galactic halos like an invisible fog. Yet here, it's clumped together in a way that defies our best simulations, a gravitational anomaly that shouldn't exist. Some astronomers suggest it could be the remnants of a smaller galaxy completely devoured by Andromeda. Its stars and gas stripped away, but its dark matter left behind, still holding the shape of its long-dead host. Others think it might be evidence of something even stranger, a flaw in our understanding of how dark matter behaves, or perhaps a hidden interaction between dark matter and forces we've yet to discover. What makes this clump so tantalizing is what it could reveal about the invisible scaffolding of the universe. If dark matter can clump this densely, it might mean galaxies grow differently than we thought, or that dark matter itself is more complex than a simple, passive backdrop. Future telescopes could study how this knot distorts light even further, peeling back the layers of its secrets. For now, it sits there, a silent, gravitational fingerprint pressing against the cosmos, reminding us just how much we still have to learn about the darkness that binds the universe together. Among the swirling mysteries of Andromeda's halo, one lonely wanderer stands out. A globular cluster adrift in the cosmic dark, untethered from the galaxy's bustling disk. Unlike the hundreds of clusters that orbit dutifully around Andromeda's core, this one moves against the tide, tracing a path so erratic it seems almost rebellious. Globular clusters are typically ancient, tightly packed families of stars, relics from a galaxy's earliest days. But this one isn't just old, it's a fugitive carrying secrets of a violent past written in the motion of its stars. What makes this cluster so extraordinary isn't just where it is, but where it's been. Its trajectory suggests it didn't form in Andromeda's halo at all. It was torn away from somewhere else, likely a smaller galaxy devoured by Andromeda billions of years ago. The stars within it tell the story. Their chemical composition doesn't match Andromeda's native clusters, hinting at an origin far outside this galaxy. It's as if we've stumbled upon a celestial orphan, a survivor of a long-forgotten collision. The cluster's age adds another layer of intrigue. At over 12 billion years old, it's one of the oldest structures we've spotted in Andromeda's vicinity, a time capsule from the universe's turbulent youth. Yet despite its age, it's remarkably intact, its stars still bound tightly together, resisting the tidal forces that should have ripped them apart. That resilience suggests something unseen might be anchoring it, perhaps a hidden knot of dark matter left behind from its original galaxy. But the real puzzle is where it's headed. Current projections show it could eventually plunge into Andromeda's disk, igniting a frenzy of new star formation, or it might sail right through, escaping the galaxy entirely. Either outcome would leave an indelible mark on Andromeda's history. For now, it drifts silently, a ghostly testament to the chaos of galactic evolution, reminding us that even the quietest corners of the universe hold echoes of cataclysmic violence. Twin neutron stars streak through Andromeda's halo like cosmic outlaws, their presence a glaring anomaly in these sparse outskirts. These remnants of massive stars that once exploded in brilliant supernovas shouldn't be here, at least not in pairs. Neutron stars are already extreme objects, packing more mass than our Sun into a city-sized sphere so dense that a single teaspoon would weigh 1 billion tons on Earth. But finding two of them locked in a ghostly dance, far from the bustling star-forming regions where they were born, forces us to rewrite what we thought we knew about stellar evolution. What makes these twin neutron stars truly baffling is their motion. Most neutron stars spin with predictable precision, like celestial lighthouses. These two, however, wobble erratically, their rotations skewed as if some violent event knocked them off balance. Their orbits around each other are equally peculiar, too tight for a typical binary system, yet too stable to have formed naturally in the halo's diffuse environment. The leading theory: they were violently ejected from Andromeda's crowded disk long ago, flung into the abyss by the gravitational chaos of a nearby supernova or a close encounter with a black hole. Yet even that explanation raises new questions. If they were ejected, why didn't the force rip them apart? Their survival suggests an almost unbreakable bond forged in the furnace of their shared past. Some researchers speculate they might be the rare survivors of a triple star system, where the third star was torn away, leaving these two locked in a gravitational embrace. Others wonder if their unusual spins hint at exotic physics, perhaps interactions with dark matter or even relics of primordial quantum forces from the early universe. Wherever they came from, their existence challenges our assumptions. Binary neutron stars are supposed to be rare in galactic halos where stellar encounters are few. Yet here they are, defying the odds and offering astronomers a front-row seat to the universe's most extreme physics. If they continue spiraling inward, their eventual collision could unleash a kilonova, a spectacular explosion that forges heavy elements like gold and platinum. For now, they drift through the halo, silent witnesses to the universe's unrelenting creativity, proving that even in the quietest corners of space, the cosmos keeps its most dazzling surprises. A ghostly river of stars winds through the darkness of Andromeda's halo, stretching nearly 200,000 light-years, a shimmering scar left behind from one of the galaxy's most violent feasts. This stellar stream isn't just a random scattering of stars, it's a cosmic crime scene, the shredded remains of a dwarf galaxy torn apart by Andromeda's immense gravity. Imagine a ribbon of starlight, so faint it's barely visible, yet so vast it dwarfs the entire Milky Way. Every star in this stream carries a chemical fingerprint, a clue pointing back to the doomed galaxy it once called home. What makes this stream so extraordinary is its structure, not a chaotic spray, but a precise, almost elegant curve, as if the gravity that ripped it apart also sculpted it into this hauntingly beautiful shape. Stars near the center of the stream move faster, while those at the edges lag behind, tracing the ghostly outline of their original galaxy like ink bleeding through water. By mapping their motion, astronomers can rewind the clock, piecing together the moment, billions of years ago, when Andromeda's tidal forces stretched this small galaxy into oblivion. But the stream tells a deeper story than just destruction. The stars within it are older and more metal-poor than most in Andromeda's disk, hinting that the devoured galaxy was ancient, a relic from the universe's earliest epochs. Its demise wasn't just a random act of violence, it was a delivery of primordial building blocks, raw material that Andromeda repurposed to grow even larger. Some of those stars may have even been hurled into the halo, forming the very clusters and clouds we've already explored, yet the most unsettling revelation. This stream isn't alone. Dozens of similar filaments likely crisscross Andromeda's halo, remnants of other galactic meals. Some may still be hidden, too faint for our telescopes to detect, waiting for future technology to expose them. Together, they paint a picture of Andromeda not as a static island of stars, but as a dynamic predator, growing by consuming its smaller neighbors, a process our own Milky Way is no stranger to. For now, this stellar river drifts silently, a testament to the slow, inevitable violence of cosmic evolution. But it's also a time capsule, preserving the history of a galaxy that no longer exists, its story written in the motion of stars that refuse to fade away. As we study it, we're not just observing destruction, we're reading the autobiography of Andromeda itself, one star at a time. Tucked away in the halo's shadowy depths, an invisible anomaly crackles with energy, a massive, shapeless blob of radio waves with no visible light to explain it. Unlike the neutron stars or stellar streams we've seen so far, this one doesn't glow in telescopes. Instead, it screams across radio frequencies, a silent but furious broadcast from the cosmos' most enigmatic corners. At first glance, it resembles the jets of supermassive black holes, those narrow beams of particles shot into space at nearly the speed of light. But here's the twist: there's no black hole nearby, no galaxy at its center. Just radio noise echoing from nothingness. The scale of this blob is staggering. Spanning hundreds of light years, it dwarfs any known black hole jet, yet it lacks the structure or focus typical of such phenomena. Its radio emissions flicker unpredictably, flaring and fading without rhythm, as if powered by some chaotic engine hidden in the dark. Some astronomers suggest it might be the remnant of an ancient eruption, a black hole's death cry from a time when Andromeda was young, its jet now dissipated into this ghostly smear. Others propose an even wilder idea: a trail of dark matter annihilation where unseen particles collide and annihilate, releasing bursts of energy we can barely detect. Then there's the most tantalizing possibility that we're seeing something entirely new. Could this blob be the signature of a primordial black hole, one that formed in the early universe and now drifts unseen, its presence betrayed only by the ripples it leaves in radio waves? Or might it be evidence of exotic physics, a particle interaction or energy source we haven't even theorized yet? The longer we stare at it, the stranger it becomes. Unlike anything in our own galaxy's halo, this feature challenges every assumption about how energy and matter behave in the void between galaxies. What makes it even more puzzling is its isolation. Most intense radio sources have clear counterparts, supernova remnants, quasars, or star-forming regions. But this one floats alone, untethered from any visible structure, as if the universe carved out a pocket of pure energy and left it adrift. Future telescopes tuned to even lower frequencies may finally decode its secrets, but for now, it remains a cosmic Rorschach test, a blur of radio static daring us to interpret its hidden story. One thing's certain: in the quiet expanse of Andromeda's halo, this invisible enigma is shouting, and we're only just beginning to listen. 3 stars blaze through Andromeda's halo at speeds so extreme they defy gravity's grasp, each one a runaway fugitive, hurtling toward intergalactic space like bullets fired from a cosmic gun. These aren't just fast-moving stars, they're hypervelocity objects ejected with such force that they'll eventually leave the galaxy entirely, destined to drift alone in the void between Andromeda and its neighbors. What's shocking isn't just their speed, thousands of kilometers per second, but the fact they're traveling together, a trio of celestial outlaws with a shared origin story written in their trajectories. The leading theory: a close encounter with Andromeda's supermassive black hole. Imagine a star system venturing too near the galaxy's central monster, its gravity slingshotting one star inward while flinging the others outward with unimaginable force. This 3-body tango could explain their synchronized escape, one star sacrificed to the black hole's appetite, while the others were ejected as gravitational shrapnel. But here's the twist: their chemistry doesn't quite match the stars near Andromeda's core. Instead, their composition suggests they might be interlopers from a smaller galaxy torn apart long ago, their chaotic orbits altered again by the black hole's pull. Their paths are even more revealing. One star races ahead, its trajectory slightly curved, as if nudged by an unseen hand, perhaps dark matter's invisible tug. The other 2 follow in a loose formation, their speeds varying just enough to hint at turbulence in the halo's gravitational field. By tracking their movement, astronomers can map the hidden forces shaping Andromeda's outskirts, uncovering pockets of dark matter or even traces of ancient collisions. But the most thrilling possibility: these stars might not be alone. If they were ejected during a violent merger, others like them could be scattered across the halo, invisible to current telescopes. Future surveys might reveal an entire population of hypervelocity stars, each one a clue to the chaotic events that shaped Andromeda's growth. For now, these 3 streak onward, their light a fleeting testament to the galaxy's violent past and a reminder that even in the stillness of space, nothing ever stands still. Amid the swirling mysteries of Andromeda's halo, one star stands apart not for its brightness or speed, but for what it lacks. This ancient giant, nearly 12 billion years old, contains barely a trace of metals, elements heavier than hydrogen and helium that fill younger stars like our Sun. In a universe where even the emptiest corners have been seeded with stardust from countless supernovae, this star is a time capsule, a relic from an era before heavy elements existed at all. What makes this star so astonishing isn't just its age, it's where we found it. Metal-poor stars typically lurk in the crowded hearts of galaxies or within dense globular clusters, trapped where the first generations of stars formed. But this one drifts alone in the sparse halo, far from the regions where such primordial objects should reside. Its very presence suggests a dramatic past. Perhaps it was hurled outward during a cataclysmic collision between Andromeda and another galaxy in the distant past, sent careening into the halo like a cosmic refugee. The star's composition tells a story of the universe's infancy. Its atmosphere contains less than 1/10,000th the metal content of our Sun, meaning it formed from nearly pure hydrogen and helium, the raw materials forged in the Big Bang. Studying it is like reading a page from the universe's first chapter, before supernova enriched the cosmos with heavier elements. Even its color is strange, slightly bluer than stars of similar age, a clue that its nuclear reactions might follow different patterns without metals to alter its internal chemistry. Yet the most tantalizing question is how it survived. Stars this metal-poor should have burned out long ago, their fuel exhausted billions of years before the Sun even ignited. But this one persists, its faint glow a testament to a slower, more efficient fusion process that defies modern stellar models. Some theorists suggest it might be a rare blue straggler, rejuvenated by stealing mass from a long-dead companion star. Others wonder if its longevity hints at unknown physics governing the earliest stars, a possibility that could rewrite our understanding of stellar evolution. For astronomers, this star is more than an oddity, it's a missing link. By decoding its light, we might finally understand how the first stars seeded the universe with the building blocks of planets, life, and everything we know. And if more like it lurk in Andromeda's halo, they could form a hidden network of cosmic artifacts, each one a silent witness to the universe's violent, creative dawn. Buried in the scattered starlight of Andromeda's halo lies the ghost of a galaxy that once was a dwarf galaxy torn apart so completely that only its debris remains, a glittering trail of stars stretched into a cosmic fingerprint. This isn't just destruction, it's a revelation. Every strewn star, every wisp of galactic rubble, acts like a breadcrumb trail, mapping the invisible forces that sculpted Andromeda's halo over billions of years. The way these stars move, the paths they trace through the darkness, they're not random, they're clues, pointing to the gravitational tides that pulled them apart. What makes this disrupted dwarf galaxy so valuable isn't just its tragedy, but its transformation. In life, it was likely a small, unremarkable galaxy, one of countless others orbiting Andromeda. But in death, it became something far more useful, a natural probe. Its stars now tracing the contours of Andromeda's gravitational field like iron filings around a magnet. By studying their motion, astronomers can reconstruct the forces at play, revealing pockets of dark matter or hidden substructures that would otherwise stay invisible. Some stars clump together, lingering in regions where gravity's grip is strongest, while others stream outward, marking where Andromeda's pull weakens. The real magic lies in the details. Stars ripped from the dwarf's outer edges now drift furthest, their slower orbits betraying the places where Andromeda's influence fades. Meanwhile, those snatched from the dwarf's core move faster, trapped in tighter, more chaotic paths, evidence of the galaxy's densest gravitational zones. Even the gaps in the stream tell a story. Where stars are missing, astronomers suspect encounters with globular clusters or dark matter clumps, gravitational encounters that scattered stars like billiard balls. But perhaps the most startling insight is how recent this destruction might have been. Unlike the ancient stellar streams we've seen before, this one shows signs of youth. Its stars haven't fully dispersed, their orbits still bearing the fresh scars of disruption. That means we might be witnessing the aftermath of a galactic meal still underway, Andromeda's gravity still feasting on the remnants. If so, it offers a rare chance to watch a galaxy grow in real time, its halo evolving before our eyes. Yet the most profound lesson here isn't about Andromeda alone. Structures like this exist around our own Milky Way, remnants of smaller galaxies it has consumed. By studying this disrupted dwarf, we're glimpsing our own galaxy's past and its future, because one day, billions of years from now, Andromeda and the Milky Way will collide, and streams like this will be all that remain of the galaxies we know today. For now, this glittering wreckage is more than debris. It's a roadmap to the forces shaping our universe, written in starlight. Deep in Andromeda's halo, a pinprick of X-ray light pulses with eerie regularity, a beacon without a visible source, blazing with the energy of a million suns, yet hidden in perfect darkness. This isn't just another stellar remnant or black hole. It's an enigma wrapped in radiation, defying every attempt to identify it. X-ray sources typically have clear counterparts: neutron stars, quasars, or binary systems where matter spirals into a dense companion. But this one flickers alone, its emissions too steady for a black hole's chaotic feast, too bright for a solitary pulsar, and too persistent for a supernova's fading echo. What makes this source so perplexing is its isolation. Most powerful X-ray emitters sit at the hearts of galaxies or within dense star clusters where fuel is abundant. Yet this one drifts in the halo's emptiness, far from any visible structure. Its emissions follow a precise rhythm, flaring every 17 hours with clockwork consistency, a cadence that rules out random cosmic collisions or one-off cataclysms. The leading theory: an orphaned intermediate mass black hole, a gravitational phantom too small to anchor a galaxy but too large to form from a single collapsed star. These rare objects are thought to lurk in halos, relics of ancient galaxy mergers, but none have ever been confirmed. If this is one, its regular flares could be the death cries of a captured star, torn apart piece by piece with each close orbit. Then there's the neutron star hypothesis, except this object emits hundreds of times more energy than any known isolated neutron star. Some researchers suggest it might be a magnetar, a highly magnetic stellar corpse, but magnetars typically flare unpredictably, not with this metronomic precision. Others propose something more exotic: a quark star, a hypothetical object so dense that neutrons themselves break down into stranger forms of matter. If real, it would be the first of its kind ever detected, challenging our understanding of how matter behaves under extreme pressures. Yet the most tantalizing possibility is that we're seeing an entirely new astrophysical phenomenon. Could this be the signature of a primordial black hole, one formed in the universe's first moments, or perhaps the aftermath of a dark matter particle annihilation event, releasing bursts of energy we've never before observed? The longer we study it, the more it resists categorization. Unlike anything in our own galaxy's halo, this X-ray source refuses to fit the mold, forcing astronomers to reconsider the boundaries of known physics. What's certain is that its very existence hints at unseen chapters in Andromeda's history. If it is a black hole, its path through the halo might trace the galaxy's violent mergers, a gravitational hitchhiker left behind from a devoured dwarf galaxy. If it's something stranger, its light could be the first glimpse of physics beyond our models. Future telescopes, tuned to higher energies or equipped with sharper resolution, may finally decode its secrets. For now, it pulses steadily onward, a cosmic metronome counting down to the moment we finally understand its rhythm. Amid the swirling chaos of Andromeda's halo, a gas cloud moves to its own rhythm, spinning backward, defiantly opposing the galaxy's rotation like a cosmic rebel. This isn't just a cloud, it's a maverick, a vast structure of hydrogen and helium stretching thousands of light years. Its motion so counter to everything around it that astronomers initially doubted their own data. Most gas in galactic halos follows the flow of their host galaxies, drifting in harmony with the gravitational tide. But this one spins the wrong way, a celestial anomaly that forces us to ask, is it an invader from beyond Andromeda, or the fallout from some catastrophic event within the galaxy itself? The cloud's backward spin is only the first clue to its strangeness. Its chemical makeup is unusually pristine, lacking the heavy elements typically forged in supernova or stellar winds. That purity suggests it didn't originate in Andromeda's star-forming regions, where gas is constantly recycled and enriched. Instead, it's more likely an outsider, a relic from a smaller galaxy, or even a wandering intergalactic cloud that wandered too close and was captured by Andromeda's gravity. Some researchers argue it could be the last gasp of a dwarf galaxy torn apart long ago. Its stars scattered while its gas lingered, still spinning with the momentum of its lost home. Yet there's another possibility, one far more violent. Simulations show that when galaxies collide, the chaos can fling gas outward with enough force to reverse its spin, sending it spiraling back against the galaxy's rotation like a boomerang. Andromeda's history is littered with such collisions. Its halo is a graveyard of devoured galaxies. Could this cloud be the aftermath of one of those ancient mergers, a splash of debris frozen in time? The answer might lie in its speed. If it's moving fast enough to escape Andromeda entirely, it's likely an intruder. But if it's bound to the halo, tracing a slow, inevitable arc back toward the galaxy, it's probably a product of Andromeda's own turbulent past. What makes this cloud so fascinating isn't just its origin, it's its fate. Gas clouds like this are fuel for future star formation, and if it eventually collides with Andromeda's disk, its backward spin could trigger spectacular shockwaves, compressing gas into new stars with unusual trajectories. Alternatively, its motion might keep it adrift in the halo indefinitely, a rogue element refusing to conform. Either way, it's a reminder that galaxies aren't static islands of stars. They're dynamic, ever-changing ecosystems where even the simplest clouds can hold the secrets of cosmic upheaval. By studying this counter-rotating enigma, we're not just solving a puzzle, we're reading the diary of Andromeda's wild, chaotic youth, written in the spin of a single, stubborn cloud. Deep in the chaotic expanse of Andromeda's halo, two unusual pairs of cosmic heavyweights lurk in the shadow's binary black hole candidates, locked in a gravitational dance where no such duet should exist. Black holes are already solitary by nature, preferring to lurk alone in the darkness, but finding not one, but two potential pairs drifting far from the galaxy's crowded core defies expectations, forcing astronomers to rewrite the rules of how these monsters form and survive in the sparse galactic outskirts. The first pair appears to be mid-weight contenders, each roughly 100 times the mass of our Sun, orbiting each other at a distance that would comfortably fit our entire solar system between them. Their presence alone is a puzzle. Binary black holes typically form in dense star clusters where frequent collisions and mergers can cram two massive objects together. But out here in the halo, stars are few and far between, making such pairings astronomically unlikely. One theory suggests they might be remnants of a globular cluster that strayed too close to Andromeda's center long ago, its stars stripped away by tidal forces while these two black holes clung together, exiled to the halo like cosmic castaways. The second pair is even stranger, one large black hole accompanied by what seems to be a smaller companion, their orbits wobbling unpredictably as if perturbed by unseen forces. The smaller object's mass fluctuates in observations, leading some researchers to question whether it's even a black hole at all. Could it be a neutron star or a rogue, ultra-dense stellar core caught in the larger black hole's grip? The way they interact suggests a violent history, perhaps a three-body encounter where a third object was ejected, leaving these two in an unstable embrace. What makes both pairs so fascinating isn't just their existence, but how they behave. Binary black holes in galactic halos should theoretically spiral inward and merge over time, yet these systems show no signs of doing so. Their orbits remain steady, as if some external force, dark matter, a passing molecular cloud, is keeping them apart. This stability is unprecedented, challenging our models of how black holes evolve in isolation. If they eventually do merge, the resulting gravitational waves would ripple across the universe, detectable by observatories millions of years from now. The real mystery is how they formed in the first place. Did they originate together in a now-vanished dwarf galaxy swallowed by Andromeda? Or were they flung outward during a close encounter with the supermassive black hole at Andromeda's core, their momentum carrying them into the halo where they now wander? Their chemistry might hold the key. By studying the faint X-ray flickers emitted as they occasionally siphon gas from their surroundings, astronomers hope to trace their origins. A metal-rich signature would hint at a birthplace near Andromeda's star-filled disk, while a pristine composition could point to an extragalactic origin. For now, these binary candidates drift silently, their true nature just out of reach, but their very presence suggests that Andromeda's halo is far more dynamic than we imagined, a place where black holes don't just fade into isolation, but sometimes find each other against all odds, rewriting the story of how galaxies evolve at their faintest edges. If more pairs like this exist, they could reveal an entirely unseen population of halo black holes, hidden architects shaping the galaxy from the shadows. A solitary shadow drifts through the emptiness of Andromeda's halo, a rogue planet untethered to any star, its surface frozen in perpetual night. This isn't just another cold, lifeless world. It's an intergalactic wanderer, a cosmic orphan that might have traveled millions of years between galaxies before Andromeda's gravity caught it. Rogue planets are rare enough within galaxies, ejected from their birth systems by violent encounters. But finding one in the halo, far from the bustling star fields of Andromeda's disk, suggests a history far more dramatic than a simple gravitational kick. What makes this object so fascinating isn't just its isolation, but what it represents. Unlike the chaotic debris of shredded galaxies or the fiery remnants of dead stars, this wanderer is eerily pristine, a frozen relic that could predate Andromeda itself. Its temperature hovers just above absolute zero, its surface untouched by stellar warmth for eons. Yet infrared observations reveal faint heat signatures, hints of a lingering internal warmth, perhaps from radioactive decay or the slow contraction of its core. Some theorists speculate it might not even be a planet at all, but a failed star, a brown dwarf too small to ignite fusion, condemned to drift in eternal twilight. The real mystery lies in its journey. How did it get here? One possibility is that it was flung outward during Andromeda's violent past, a casualty of some long-forgotten celestial close call. But its trajectory tells a different story. Moving against the halo's typical currents, its path suggests an extragalactic origin, a traveler from another galaxy entirely, hurled into the void during a cosmic collision billions of years ago. If true, it would make this object one of the few confirmed intergalactic interlopers, a silent witness to the universe's vast, untamed mobility. Yet the most tantalizing question isn't where it came from, but what surrounds it. Rogue planets are thought to sometimes retain moons or even thick atmospheres trapped in icy suspension. If this wanderer harbors such companions, they could be time capsules preserving chemistry from a foreign galactic environment. Some researchers even suggest that under the right conditions, such a planet might host subsurface oceans, kept liquid by tidal forces or residual heat, a long shot but not impossible. For now, it drifts unseen, detectable only by the faintest gravitational tug on distant starlight. but its existence hints at a hidden population of such nomads, a sea of dark worlds threading the spaces between galaxies. Every rogue planet discovered is a reminder that the universe is far more restless than we imagine, with countless unseen travelers charting their own lonely courses through the dark. And if this one could speak, its story might rewrite what we thought we knew about how galaxies grow, not just by swallowing stars, but by catching the strays of the cosmos, one frozen wanderer at a time. Far beyond Andromeda's halo, a brilliant quasar flickers like a cosmic lighthouse, its light slicing through the galaxy's outskirts before reaching our telescopes. This isn't just a distant beacon, it's the universe's ultimate backlight, illuminating Andromeda's hidden gas structures in ways nothing else could. Quasars are among the brightest objects in existence, powered by supermassive black holes devouring matter at incredible rates. But this particular one holds special value. Its alignment makes it pierce Andromeda's halo at a perfect angle, turning its beam into a diagnostic tool that reveals the invisible. As the quasar's light journeys toward us, it doesn't pass through empty space. Andromeda's halo is filled with diffuse, ionized gas, a fog so thin it would seem transparent, except for how it subtly alters the quasar's light. Every element in that gas absorbs specific wavelengths, leaving dark fingerprint lines in the quasar's spectrum. By analyzing these absorption lines, astronomers can map the halo's composition, temperature, and even motion. Some gas clouds are racing toward us, others speeding away, evidence of chaotic turbulence from ancient galactic collisions or outflows from Andromeda's disk. The most striking discovery, vast filaments of gas stretching far beyond where models predicted, some reaching distances that would engulf the Milky Way if placed in our sky. These structures aren't random, they trace the paths of dwarf galaxies devoured long ago, their gas stripped and stretched into luminous rivers by Andromeda's gravity. Other patches glow unnaturally, ionized by radiation from long-dead stars or perhaps even by dark matter interactions we don't yet understand. What makes this quasar so invaluable is its flickering. Unlike steady cosmic lights, its brightness fluctuates over months, an effect caused by clumps of matter spiraling erratically into its central black hole. Each flicker acts like a strobe, illuminating different layers of Andromeda's halo in rapid succession. By comparing snapshots taken during bright and dim phases, researchers can reconstruct a 3D map of the halo's gas distribution, revealing pockets of density that would otherwise stay hidden. Yet the true marvel lies in what this backlit halo tells us about Andromeda's future. The sheer volume of ionized gas suggests the galaxy is still growing, siphoning material from intergalactic space or cannibalizing smaller neighbors. Some of this gas will eventually spiral inward, fueling new stars, meaning Andromeda's halo isn't just a relic of the past, but a reservoir for its next chapter. And thanks to this flickering quasar, we're watching that story unfold in real time, one beam of stolen light at a time. Glittering in the void of Andromeda's halo like a cosmic jewel, a lone white dwarf star defies the ordinary, its core frozen into a crystalline lattice of carbon and oxygen, the universe's largest diamond. This isn't just a dead star, it's a celestial artifact, a relic of stellar alchemy so precise it transformed a once blazing sun into a cosmic gemstone. White dwarfs are common, the leftover cores of stars like our sun, but this one is different. Most cool into dense, dark embers over billions of years, fading quietly into the night. This one, however, has crossed a threshold few stars ever reach. Its core has solidified, freezing into a structure resembling Earth's diamonds, but scaled to planetary proportions. The process behind this transformation is as mesmerizing as the result. For eons, the star burned steadily, fusing hydrogen and helium until it exhausted its fuel. Shedding its outer layers, it left behind a searing hot core, a sphere of carbon and oxygen crushed to unimaginable densities by gravity. Over time, this core cooled, its atoms slowing until they locked into place, forming a crystalline structure trillions of times larger than any diamond on Earth. The physics at play here are extreme pressures so intense that electrons are stripped from their atoms, creating a quantum sea of particles that gradually freeze into this strange metallic state. What makes this diamond star truly remarkable is its age. White dwarfs typically take tens of billions of years to crystallize, far longer than the current age of the universe. Yet here it sits, cold and silent, its existence hinting at an even wilder possibility, that this star might be older than we thought. Some researchers suggest it could be a primordial white dwarf, born from one of the universe's first stars, its early formation giving it a head start on cooling. Others propose it might have been part of a binary system, its outer layers stripped away prematurely by a companion star, exposing its core to faster cooling. Either way, its crystalline heart offers a rare glimpse into the ultimate fate of stars, ours included. Yet the diamond star's journey doesn't end with its transformation. Crystallization releases latent heat, causing a final burst of warmth before the star settles into eternal cold. Infrared observations reveal this star is in that exact phase, its surface still glowing faintly from the energy of its atomic rearrangement. In time, even that glow will fade, leaving behind a perfect dark crystal adrift in the halo, invisible but for the subtle way it bends the light of distant stars. The implications stretch beyond mere curiosity. By studying this star, astronomers can test theories about stellar evolution, quantum mechanics, and even the timeline of the cosmos itself. Its composition, nearly pure carbon and oxygen, mirrors what our sun will become billions of years from now, a chilling preview of our own solar system's destiny. And if more like it exist in Andromeda's halo, they could form a hidden network of cosmic timekeepers, their frozen hearts recording the eons like geological strata. For now, this diamond star drifts silently, its brilliance not in light but in structure, a monument to the universe's ability to forge beauty even in death. It's a reminder that the end of a star isn't an erasure but a transformation, one that turns the ordinary into the extraordinary and the familiar into the sublime. Two stellar fugitives race through Andromeda's halo, not intact stars, but the scattered remnants of titanic explosions, each a supernova that died with a roar yet continues its journey through the galaxy's outskirts. These aren't just random stellar ghosts, they're paired phenomena, their debris clouds moving in eerie synchrony despite originating light years apart. Most supernova remnants stay near their birthplace, their shockwaves expanding into the surrounding space. But these two are different. They're runaway remnants, their debris accelerated to incredible speeds by forces we're only beginning to understand. The first runaway supernova leaves behind a vast, twisted wreckage of glowing filaments, evidence of a thermonuclear detonation so violent it should have obliterated everything nearby. Yet its debris doesn't radiate outward in a neat sphere. It streaks through the halo like a cosmic comet tail, stretching over hundreds of light years. The likely culprit, a companion star that survived the blast, its gravity warping the debris into this unusual shape while simultaneously acting as a gravitational slingshot, hurling the remains away at blistering speeds. The surviving star, now a rogue white dwarf, continues its own solitary journey through the halo, though whether it triggered its partner's destruction or merely escaped the aftermath remains one of Andromeda's lingering mysteries. The second runaway is more enigmatic still. Its debris cloud moves even faster, its shockwaves plowing through the halo's sparse gas like a ship's bow wave. The nebula left behind isn't symmetrical but fragmented, as if something tore through it long after the initial explosion. Here, the leading theory takes a darker turn. This supernova might have been part of a binary system orbiting Andromeda's central black hole. When one star exploded, the black hole's gravity flung the remnants outward violently enough to escape entirely, leaving this distorted trail of cooling gas in its wake. Supporting this idea are faint X-ray emissions along the nebula's edges, hotspots where debris collides with interstellar material at nearly 10% the speed of light. What binds these two runaways together besides their shared velocity is the ripples they've left in their passing. Behind each one, shockwaves have compressed nearby gas, triggering faint star formation in regions otherwise too sparse for such activity. It's as if they're sowing seeds of new stellar life even in death. Their paths also trace hidden currents in the halo, revealing gravitational eddies and turbulence that would otherwise be invisible. By studying their movement, astronomers can reconstruct the halo's unseen structure, mapping dark matter concentrations or even remnants of ancient galactic collisions that still influence motion today. The ultimate mystery, though, is where they're headed. Unlike stars whose trajectories can be predicted for millennia, supernova remnants interact with their environment, their debris slowing over time. Yet these two show little deceleration, their momentum carrying them ever outward. One might eventually escape Andromeda entirely, becoming an intergalactic wanderer. The other could intersect with a passing molecular cloud, igniting a new wave of star formation, or perhaps plunge back into the galaxy's disk, its heavy elements enriching future generations of stars. Their stories remind us that a star's death isn't an end but a transformation. These runaway remnants aren't just relics, they're cosmic sculptors, shaping the galaxy in ways we're only beginning to measure. And in their fleeting glow, they illuminate not just Andromeda's present, but the invisible forces that have guided its evolution for billions of years. In the vast star-sparse reaches of Andromeda's halo, something unseen tugs at the cosmos, a gravitational whisper where there should be light. This isn't just an empty patch of sky, it's a cosmic phantom, a region where stars move as if orchestrated by an invisible conductor. Their trajectories curve too sharply, their speeds too uniform, all hinting at the presence of a hidden structure, one that could rewrite our understanding of how galaxies form. Astronomers call it a dark galaxy candidate, a dwarf galaxy so dominated by dark matter that its stars are mere afterthoughts, scattered specks drowning in an ocean of unseen mass. What makes this candidate so compelling is how perfectly it fits and yet defies our expectations. Dwarf galaxies typically contain millions of stars, enough to glow faintly against the void. But here, the starlight is pitifully sparse, far too meager to account for the gravitational forces at play. The handful of visible stars act like buoys floating on an invisible current, their paths revealing the outline of something far more massive lurking beneath. Simulations suggest this could be a galaxy that never truly ignited, a failed structure where dark matter clumped together as usual, but star formation fizzled, leaving behind a cosmic shadow. The implications are staggering. If confirmed, this dark galaxy would be one of the purest dark matter laboratories in the universe, a place where the mysterious substance isn't just present but overwhelmingly dominant. Unlike typical galaxies where dark matter mingles with gas and stars, here it might exist almost undisturbed, its behavior pristine and unaltered by messy astrophysical processes. Studying it could reveal dark matter's properties in unprecedented detail: how it clumps, how it interacts with itself, even how it shapes the birth of galaxies. Yet the mystery deepens when we ask how such a structure survived. Galactic halos are harsh environments where tidal forces from the host galaxy shred fragile dwarfs over time. That this dark candidate endures suggests an incredible density. Its dark matter packed so tightly that Andromeda's gravity can't tear it apart. Some researchers speculate it might be wrapped in a protective shell of even darker material, a phenomenon predicted by certain exotic dark matter theories. Others wonder if it's not a survivor at all, but a newcomer, a captured galaxy from another group, flung into Andromeda's halo by some long-ago cosmic collision. The search for answers hinges on the stars themselves. Each one is a tracer, its motion a clue to the unseen mass guiding it. By mapping their velocities with precision, astronomers can reconstruct the dark galaxy's shape, whether it's a flattened disk, a puffed-up sphere, or something more irregular. Already, the data suggests a bizarre profile. The dark matter isn't distributed smoothly, as in most galaxies, but lumped in dense knots like unseen mountains in an invisible landscape. But the most tantalizing possibility isn't just what this object is, it's what it represents. If one dark galaxy exists, there could be hundreds, even thousands, drifting unseen throughout Andromeda's halo and beyond. These hidden structures might be the missing pieces in our cosmic census, the invisible scaffolding that explains why galaxies rotate the way they do or how the universe's large-scale structure took shape. They could even be the key to understanding dark matter's true nature, whether it's cold, warm, or something stranger still. For now, this ghostly candidate remains just out of reach, its existence hovering between theory and confirmation. Future telescopes like the upcoming Nancy Grace Roman Space Telescope might finally pierce the veil, spotting fainter stars or even the faintest wisp of gas that could seal its identity. Until then, it lingers as a gravitational riddle, a shadow in the halo that refuses to be ignored, a reminder that the universe's greatest secrets don't always shine. They lurk, stretching across the unimaginable void between galaxies. A faint, thread-like tendril of gas and dark matter weaves through Andromeda's halo, one delicate strand in the universe's grand tapestry. This isn't just a wisp of leftover material. It's a cosmic filament, part of the vast scaffolding that binds galaxies together in an intricate web spanning billions of light years. Most of these filaments remain invisible, their presence betrayed only by the gravitational pull they exert on the galaxies they connect. But this one, illuminated by the glow of ionized hydrogen and backlit by distant quasars, offers a rare glimpse into the hidden architecture of the cosmos. The filament structure is deceptively simple, a river of gas so diffuse it would seem almost empty, if not for the way it tugs at Andromeda and its neighboring galaxies, guiding their motion like celestial marionettes. Dark matter makes up most of its mass, an invisible skeleton wrapped in tendrils of hydrogen older than the stars themselves. This gas isn't pristine, it carries traces of heavier elements, hinting that it's been recycled through generations of stars, ejected in supernova, and swept up again in the relentless flow of the cosmic web. Somewhere along its length, dwarf galaxies and star clusters cling like beads on a string, their orbits tracing the filament's curve as if pulled by an unseen current. What makes this filament extraordinary isn't just its existence, but its role in Andromeda's evolution. Filaments like this are the universe's delivery system, funneling gas and smaller galaxies into larger ones, fueling star formation and galactic growth over eons. Simulations suggest Andromeda owes much of its size to these cosmic highways, which have fed it a steady diet of material since its birth. Even now, the filament hums with quiet activity, gas slowly draining toward Andromeda's gravitational well, dark matter subtly reshaping the orbits of passing stars, and the occasional dwarf galaxy slipping inexorably closer to its eventual merger. Yet the filament's fate is uncertain. Over time, the relentless expansion of the universe could stretch it to the breaking point, thinning its gas until it dissipates into the void. Alternatively, a collision with another filament might compress it, triggering bursts of star formation in the galaxies it connects. Already, there are signs of turbulence knots where gas densities spike, possibly the seeds of future stellar nurseries or even new dwarf galaxies in the making. For astronomers, this filament is more than a curiosity. It's a living blueprint. By studying its structure, they can test theories about how dark matter shapes the universe, how galaxies communicate across vast distances, and even how the first structures formed after the Big Bang. Its very presence is a reminder that galaxies aren't isolated islands, they're nodes in a vast dynamic network, linked by threads of darkness and light. And as we trace its path, we're not just mapping Andromeda's past, we're reading the universe's story, written in gas and shadow. Deep in the halo's shadowy expanse, a cosmic metronome ticks with imperfect rhythm, a pulsar whose beacon-like pulses arrive just a fraction too late, as if the universe itself is slowing its message. Pulsars are nature's most precise clocks, spinning neutron stars that beam radiation with such regularity you could set your watch by them. But this one defies the pattern. Its signals stagger, delayed by milliseconds, an astronomical hiccup that shouldn't exist. The culprit, something invisible, something vast, the halo's ghostly gas, warping the pulsar's light as it travels toward us, revealing a hidden landscape of turbulence and structure we can't otherwise see. These delays aren't random. They follow a pattern, a subtle ebb and flow that maps the density of the gas the pulses must traverse. Each millisecond lag is a clue, a fingerprint of the halo's otherwise undetectable medium. As the pulsar's beams slice through the halo, they encounter pockets of ionized hydrogen so sparse they'd qualify as a vacuum on Earth. Yet over tens of thousands of light years, their cumulative effect bends and slows the signal like light passing through frosted glass. The denser the region, the greater the delay. By tracking these fluctuations, astronomers have reconstructed the halo's secret topography, uncovering waves and ripples in the gas that suggest past collisions or outflows from Andromeda's star-forming regions. But the real intrigue lies in what these distortions imply about the halo's evolution. The delays aren't static, they shift over years, hinting that the gas isn't just drifting passively but churning with unseen energy. Some researchers theorize this turbulence might be fueled by dark matter interactions, its gravitational nudges stirring the gas like an invisible spoon. Others point to faint, distant supernovae, their shockwaves rippling through the halo long after the stars themselves have faded. The pulsar's hiccups could even trace the footprints of ancient dwarf galaxies, their orbits disturbing the gas like stones dropped into a pond. Then there's the tantalizing possibility that we're witnessing something even more profound. Quantum physics predicts that empty space isn't truly empty. It's a seething foam of virtual particles that flicker in and out of existence. Could this pulsar's delayed signals be the first evidence of these quantum effects operating on a galactic scale? It's a long shot, but if true, it would mean this humble pulsar isn't just a victim of halo gas, it's a probe of the universe's most fundamental fabric. For now, the time-delayed pulsar remains a puzzle wrapped in a mystery. Every pulse it sends is a message in a bottle, distorted by its journey through the halo's unseen currents. And as we decode those distortions, we're not just studying a distant neutron star, we're reading the diary of Andromeda's halo, written in the language of bent light and borrowed time. 3 rogue star clusters streak through Andromeda's halo like cosmic fugitives exiled from the galaxy's bustling disk and hurled into the darkness beyond. These aren't just wandering groups of stars, they're celestial outlaws, each carrying a distinct chemical fingerprint that tells the story of their violent ejection. Unlike the ancient globular clusters that have always called the halo home, these 3 are younger, their stars rich in metals forged in Andromeda's recent stellar nurseries. Their very existence challenges our understanding of how galaxies shed their inhabitants, revealing a process far more chaotic than we ever imagined. The first cluster moves with unsettling speed, its stars bound together so tightly that the galaxy's gravity couldn't tear them apart during their expulsion. Spectroscopy reveals an unusual mix of elements, elevated levels of europium and gold, metals typically forged in rare, cataclysmic neutron star collisions. This suggests the cluster originated near Andromeda's crowded core, where such violent events are more common. Yet its trajectory points to a dramatic exit, possibly triggered by a close encounter with the supermassive black hole at Andromeda's heart. Simulations show that when star clusters pass too near these gravitational monsters, they can be ripped apart or, in rare cases, flung outward intact like celestial slingshots. Cluster 2 tells a different story. Its stars are oddly synchronized, all rotating around a shared axis with eerie precision. This level of coordination is unheard of for exiled clusters. Most are left tumbling chaotically after ejection. The key may lie in its chemistry, an overabundance of carbon and nitrogen, elements typically enriched by red giant stars. This hints that the cluster was born in one of Andromeda's dense molecular clouds before being expelled by a shockwave, perhaps from a nearby supernova or the gravitational wake of a passing dark matter clump. The explosion or disturbance would have acted like a cosmic catapult, launching the cluster outward while preserving its internal order. Then there's the third cluster, the true Enigma. Unlike the others, it's not moving away from Andromeda's disk, but in a wide, looping orbit that will eventually bring it back. Its stars show extreme oxygen enhancement, a signature usually found in stellar nurseries exposed to multiple generations of supernova. Even stranger, the cluster's outer stars are evaporating, leaving behind a glowing trail of ionized gas like a comet's tail. The leading theory: this cluster didn't just get ejected, it's still under siege. Something in the halo is stripping it apart, possibly a previously unknown stream of high-energy particles or an encounter with an invisible dark matter substructure. Together, these three clusters paint a picture of Andromeda's disk as a place of relentless upheaval, where star clusters aren't just born but sometimes banished. Their varied fates demonstrate how galactic evolution isn't always a gradual process. It can be abrupt, violent, even capricious. Some clusters escape cleanly, others are mangled in the process, and a few become trapped in gravitational purgatory, neither fully free nor fully bound. What they share is rarity. Finding even one such ejected cluster is unusual. Spotting three in Andromeda's halo suggests the galaxy's disk might be far more dynamic than we realized, routinely flinging out stellar families through mechanisms we've only begun to understand. Future observations could reveal dozens more, each with its own story of exile written in starlight. For now, these three serve as reminders that galaxies aren't static museums. They're living, breathing engines of creation and destruction, where even the stars can become wanderers against their will. At the very edge of detectability, where starlight fades into the noise of the cosmos, something haunts Andromeda's halo. A smudge of light so tenuous that astronomers still argue whether it's real. This phantom dwarf galaxy, if it exists at all, teeters between discovery and illusion, its presence inferred from the faintest whispers of data. Unlike the obvious, glittering dwarfs that orbit Andromeda, this one clings to the threshold of visibility, a cosmic maybe that challenges the limits of our telescopes and our patience. The evidence is maddeningly ambiguous. Some observations reveal a sparse cluster of ancient stars moving in concert, their synchronized motion hinting at gravitational unity, the hallmark of a dwarf galaxy. But the light is so dim, so scattered, that it could just as easily be a chance alignment of unrelated stars drifting through the halo. The debate hinges on a handful of pixels in deep field images, where statistical noise blurs the line between signal and artifact. Even the star's chemical signatures offer mixed clues. Their metal-poor composition suggests antiquity, typical of dwarf galaxies, but their distribution lacks the dense core expected of such structures. What makes this potential dwarf so compelling isn't just its elusiveness, it's what its existence or absence would imply. If real, it could be a dark galaxy in the truest sense, its starlight a feeble afterthought compared to its dark matter content. Simulations predict that Andromeda's halo should swarm with hundreds of such faint dwarfs, remnants of the universe's smallest building blocks, yet we've found only a fraction of that number, leaving a gap in our cosmic census. This phantom could be one of the missing pieces, a ghostly testament to the legions of dwarfs that theory says should be there but remain stubbornly unseen. Then there's the tantalizing possibility that we're seeing it at all wrong. Some researchers propose an even wilder interpretation. This smudge might not be a dwarf galaxy, but a tidal dwarf, a temporary structure birthed from the debris of two colliding galaxies, a celestial soap bubble doomed to pop. Unlike traditional dwarfs which form in dark matter halos, tidal dwarfs are knitted together by gravity from cast-off gas and stars, lacking dark matter entirely. If confirmed, it would make this object a cosmic impostor, a fleeting mimic of the real thing. The hunt for answers plays out in the nuances of instrumentation. New telescopes like the upcoming Vera C. Rubin Observatory promise to settle the debate with unprecedented sensitivity, either pinning down the dwarf's existence or consigning it to the graveyard of observational glitches. Until then, it lingers in the realm of almost a reminder that the universe's most profound mysteries often lurk in the gaps between what we can see and what we can almost see. And whether it's a shadow or a revelation, this phantom has already taught us something vital. Sometimes the faintest whispers lead to the loudest questions. Hidden within the sparse expanse of Andromeda's halo, an invisible force bends the rules of cosmic magnetism, a vast region where magnetic fields align with eerie uniformity, forming a skeleton of power that could shape the galaxy's future. Magnetic fields permeate every corner of the universe, but here they twist into something unusual, an organized lattice stretching tens of thousands of light years, its strands vibrating with energy far stronger than typical for such a diffuse environment. This isn't random chaos, it's a scaffold of force, one that might hold the key to how Andromeda births its next generation of stars. What makes this magnetic anomaly so striking is its structure. Normally, magnetic fields in galactic halos tangle like loose yarn, their directions scrambled by turbulence and time. But in this region, they've somehow combed into parallel lines as if smoothed by an unseen hand. The fields aren't just orderly, they're intense, packing enough energy to potentially resist the halo's chaotic motions. Some astronomers suggest this alignment could be the aftermath of a colossal collision, where two dwarf galaxies merged long ago, their combined magnetic fields stretched and straightened in the violence of the encounter. Others speculate it's a relic from Andromeda's infancy, a primordial magnetic imprint frozen in time, preserved by the halo's stillness. The true fascination lies in what these fields might do next. Magnetic fields are star formation's invisible choreographers. They guide collapsing gas clouds, slow their spin, and help them coalesce into new suns. In Andromeda's disk, where gas is dense, this process is well understood. But in the halo, where material is thin and scattered, these aligned fields could act like cosmic rails, channeling sparse gas into unexpected pockets over millions of years. Simulations show that under the right conditions, such fields might trigger star formation in places we'd otherwise consider barren, creating sparse, wandering stellar families far from the galaxy's bustling center. Yet the anomaly's influence might not stop there. These magnetic strands could also shield pockets of gas from the halo's harsh environment, where radiation and turbulence would otherwise tear star-forming clouds apart. Imagine a fragile cocoon of gas wrapped in magnetic armor, slowly contracting until against all odds it ignites into new stars. If this process is underway, we might already be seeing its early results. Young, isolated stars flickering in the halo's depths, their presence otherwise inexplicable. The most tantalizing possibility, this magnetic scaffold could be a snapshot of the future. As Andromeda continues to consume smaller galaxies and absorb intergalactic gas, these fields might funnel incoming material into specific regions, steering the galaxy's growth in ways we've never before observed. Over billions of years, they could sculpt Andromeda's halo into something far more structured and far more alive than we ever imagined. For now, the anomaly remains a whisper in the data, its full scope still emerging as telescopes grow more sensitive to magnetism's subtle signatures. But one thing is certain, in the quiet expanse of the halo, forces are at work that we're only beginning to understand, and their ripples could echo through Andromeda's story for eons to come. At the very edge of Andromeda's halo, where stars thin to near nothingness and gas clouds fade into the void, lies an absence so profound it feels intentional, a vast spherical region nearly empty of matter, stretching tens of thousands of light years across. This isn't just a quiet corner of space. It's the great Andromeda void, a cosmic desert so barren it defies the very nature of galactic halos, which are typically littered with the debris of ancient collisions and star formation. Its emptiness isn't just unusual, it's unsettling, as if the universe carved out a pocket of nothing and left it there as a riddle. The void's edges are eerily sharp, as though traced by some unseen boundary. Within its confines, even the sparse background stars that dot the halo seem to avoid crossing its threshold, their paths bending slightly around it like water diverting around a stone. Some researchers argue this could be evidence of a primordial flaw in the fabric of space-time, a relic from the universe's infancy, when quantum fluctuations during the Big Bang left behind bubbles of anomalous structure. If true, this void might be a fossil, a preserved pocket of the early cosmos where matter simply never coalesced, untouched by the gravitational tug of war that shaped everything around it. But the more chilling possibility is that this emptiness wasn't always so. Simulations suggest it might be the scar of a cataclysmic encounter, where a dwarf galaxy packed with dark matter plowed through Andromeda's halo like a bullet, its gravity sweeping the region clean of gas and stars in its wake. The aftermath would resemble a ship's bow wave frozen in time, except here the wave is an absence, a ghostly imprint of destruction. Supporting this idea are faint, distorted streams of stars at the void's periphery, their orbits twisted as if recoiling from some ancient violence. Then there's the dark matter factor. If the void contains even a trace of the invisible substance undetectable to our telescopes, its gravitational pull could be subtly sculpting the motions of stars far beyond its borders. Some models propose that dark matter might cluster differently in such voids, forming intricate web-like structures that repel ordinary matter rather than attracting it. If that's the case, this region isn't truly empty. It's a hall of mirrors filled with forces we're only beginning to fathom. The most tantalizing question isn't what the void is, but what it means for Andromeda's future. Voids aren't static, they grow, their boundaries shifting as the universe expands. If this one continues to stretch, it could one day sever entire sections of Andromeda's halo, isolating stars and gas clouds in island realms cut off from the galaxy's main body. Alternatively, infalling gas from intergalactic space might eventually flood the void, igniting a wave of star formation that erases its emptiness entirely. For now, the great Andromeda void remains a silent enigma, a blank space on the cosmic map that refuses to be filled. Whether flaw or scar, it's a reminder that even in the densest corners of the universe, nothingness can be just as telling as presence, and that some of the cosmos' loudest statements are written in the language of absence. The scattered oddities of Andromeda's halo aren't just isolated curiosities, they're pages torn from the galaxy's violent biography, each one bearing the scars of cosmic collisions and stellar upheavals that shaped Andromeda into the Titan we see today. Picture the halo as a celestial crime scene where every rogue star cluster, every twisted magnetic field, and every phantom galaxy whispers clues about the catastrophes that forged them. Taken together, they reveal a history written in gravitational chaos, one where Andromeda didn't grow gently, but through a relentless series of mergers, explosions, and tidal disruptions that left their mark in the most unexpected ways. Start with the stellar streams, those shimmering ribbons of stars winding through the darkness. Like scars mapping the path of a long-healed wound, they trace the orbits of galaxies Andromeda consumed over billions of years. But these aren't just random splatters of debris. The chemistry of their stars tells us when and how their parent galaxies died. Metal-poor streams, like the one we explored earlier, are the bones of ancient dwarfs, galaxies so old they formed when the universe was still a toddler. Their stars carry almost no heavy elements because they were born before supernova had seeded the cosmos with metals. By contrast, younger streams glow with the fingerprints of more recent collisions, their stars enriched by generations of stellar explosions before their galaxies were torn apart. Then there are the rogue globular clusters, dense knots of stars hurtling through the halo like celestial fugitives. These aren't native to Andromeda's halo at all. Their unusual orbits and chemical makeup betray them as invaders, snatched from smaller galaxies during violent mergers. Some still cling to traces of dark matter from their original homes, ghostly anchors that help them survive the tidal forces that should have ripped them apart. Their very existence confirms that Andromeda didn't just swallow galaxies whole. It stripped them layer by layer, leaving their star clusters stranded in the halo like shipwrecks on a cosmic shore. But the halo's story isn't just about destruction. Hidden in its depths are clues to periods of frenzied creation. The counter-rotating gas cloud we encountered earlier, spinning backward against Andromeda's motion, might be the fallout from a head-on collision with another galaxy, a crash so violent it sent shockwaves of gas recoiling into the halo. That gas didn't just sit there. Models show it likely fueled bursts of star formation in the halo's sparse reaches, explaining the presence of young, metal-rich stars far from the galaxy's bustling disk. Even the mysterious X-ray source pulsing in the darkness could be a relic of these ancient fireworks, a black hole or neutron star hurled into the halo during the chaos of a merger. Perhaps most telling are the dark matter clumps and phantom dwarfs, structures so faint they barely register in starlight, yet whose gravity betrays their presence. These are the ghosts of failed mergers, galaxies so thoroughly dismantled that only their dark matter skeletons remain. Their distribution reveals how Andromeda's halo grew hierarchically, with smaller structures merging to form larger ones, leaving behind a web of dark matter that still shapes the motion of visible stars today. The fact that some of these clumps are denser than expected suggests Andromeda's appetite for smaller galaxies was even more voracious than we thought, its gravity tearing them apart but preserving their dark cores like cosmic trophies. The halo's greatest irony, its apparent stillness, is an illusion. Though it looks sparse and tranquil today, every object within it, from the diamond-crusted white dwarf to the hypervelocity stars racing toward intergalactic space, is a testament to the galaxy's violent, dynamic past. Even now, the halo is evolving. New streams are forming as Andromeda continues to cannibalize smaller galaxies, while old ones slowly dissolve into the background. Gas from these collisions is still settling, magnetic fields are realigning, and dark matter is shifting in response to the galaxy's growth. Far from being a relic, the halo is a living archive, its contents constantly rewriting their own histories as they journey through Andromeda's gravitational embrace. What emerges from this tapestry isn't just Andromeda's story, but a preview of our own galaxy's fate. The Milky Way's halo likely holds similar wreckage from its own mergers, and in a few billion years, when Andromeda and the Milky Way collide, their halos will mingle too, scattering new streams and rogue clusters into an even vaster expanse. By studying Andromeda's halo today, we're not just piecing together its past, we're reading the future written in starlight, a future where galaxies aren't islands but destinations, linked by bridges of debris spanning the dark. For all the discoveries we've made about Andromeda's halo, its strangest inhabitants continue to defy explanation, each one a puzzle that chips away at our understanding of how galaxies work. Take the backward spinning gas cloud, a structure so massive yet so pristine it shouldn't exist in a galaxy this evolved. Why hasn't it mixed with Andromeda's other gases? What launched it into its counter-rotating orbit with enough force to resist the halo's gravitational tides? Current models of galactic collisions can't fully account for its properties, leaving astronomers to wonder if we're missing a fundamental piece of how galaxies absorb smaller neighbors, or if this cloud hints at entirely new physics governing gas dynamics in the cosmic void. Then there's the pulsar whose signals arrive mysteriously delayed, as if the space between us is thicker than it should be. The leading theory suggests invisible clouds of ultra-diffuse gas are slowing its radio pulses, but these clouds would need densities far lower than anything we've observed elsewhere. Could this be evidence of quantum vacuum fluctuations acting on galactic scales, a phenomenon predicted by theory but never before detected? Or is the pulsar's path threading through pockets of dark matter that interact with light in ways we don't yet understand? Every anomalous delay in its rhythm forces us to reconsider what empty space truly contains. The rogue neutron star duo presents another enigma. These extreme objects, each heavier than our sun yet small enough to fit inside a city, somehow survived a journey that should have torn them apart. Their synchronized escape from Andromeda's disk suggests a shared violent origin, possibly a run-in with the supermassive black hole at the galaxy's core. But simulations struggle to reproduce their current orbits without invoking unknown forces. Some physicists speculate their bizarre wobbles could trace back to quantum vortices in their superfluid cores, while others propose their trailing clouds of exotic matter that subtly alter their motion. Without closer study, they remain gravitational riddles wrapped in magnetic mysteries. Perhaps most perplexing of all is the dark galaxy candidate, a gravitational signal without enough starlight to explain it. If confirmed, this object would be the purest dark matter laboratory in the known universe, untouched by the messy astrophysics that complicates studies in brighter galaxies. Yet its very existence challenges our models of how dark matter clumps. Shouldn't such dense concentrations have birthed stars? The absence of visible light suggests dark matter might behave differently at small scales, potentially hinting at multiple dark matter particle types or even unseen interactions between dark matter and dark energy. And then there are the questions we haven't even thought to ask yet. Why do some stellar streams show gaps where stars are conspicuously absent? Could these be signs of intermediate mass black holes wandering unseen through the halo, their gravity plowing voids in the stellar flows? What powers the radio blob with no apparent energy source? Even Andromeda's ordinary halo objects like the ancient metal poor stars or disrupted dwarf galaxies hold surprises, their orbits subtly deviating from predictions in ways that suggest our map of the halo's dark matter distribution is woefully incomplete. Each mystery is more than a curiosity, it's a potential revolution waiting to happen. The halo's oddities don't just challenge individual theories, they probe the boundaries of cosmology itself, from quantum mechanics to galactic evolution. Future telescopes may solve some puzzles while unveiling others, but one thing is clear: Andromeda's halo isn't just a collection of cosmic leftovers. It's a frontier where the known universe meets the undiscovered, and every strange object is a signpost pointing toward deeper truths we've only begun to glimpse. The secrets of Andromeda's halo won't stay hidden forever. New eyes are preparing to peer deeper into its mysteries than ever before. Leading the charge is the James Webb Space Telescope, already revolutionizing infrared astronomy with its piercing gaze. Unlike Hubble, which revealed much of the halo's large-scale structure, Webb detects the faintest heat signatures from objects too cold or distant to emit visible light. That means rogue planets floating in the darkness, nearly invisible star clusters, and even diffuse gas clouds could soon step into the spotlight. Webb's instruments are particularly suited to studying the halo's chemical makeup, potentially identifying heavy elements in stellar streams that would reveal exactly which types of galaxies Andromeda consumed to grow so large. But Webb is just the beginning. The upcoming Nancy Grace Roman Space Telescope, set to launch later this decade, will map Andromeda's halo with unprecedented breadth and precision. Roman's wide-field surveys will cover vast swaths of sky in single observations, making it ideal for spotting more hypervelocity stars, tracing the full extent of stellar streams, and potentially confirming the existence of those elusive dark galaxy candidates. Its coronagraph instrument might even directly image rogue planets or brown dwarfs drifting through the halo, objects currently too dim for other telescopes to resolve. Where Webb zooms in, Roman pulls back, revealing how all the halo's oddities connect in a single, sprawling web. On the ground, next-generation observatories like the extremely large telescope ELT will add another dimension to the hunt. With a mirror nearly 30 meters across, 3 times wider than today's largest optical telescopes, the ELT could resolve individual stars even in Andromeda's most distant halo regions. Its spectrographs will measure stellar motions with pinpoint accuracy, allowing astronomers to reconstruct the orbital paths of runaway star clusters or map the gravitational influence of dark matter clumps in real time. Combined with adaptive optics to cancel out atmospheric distortion, the ELT might finally catch halo objects in the act of changing, watching as stellar streams stretch or gas clouds collide over human timescales. Radio astronomy isn't being left behind either. The Square Kilometre Array (SCAR), an international effort to build the world's largest radio telescope, will probe the halo's magnetic fields and diffuse gas with sensitivity 100 times greater than current instruments. Those faint pulsar delays we discussed earlier, the SKA could detect them with such precision that we might pinpoint exactly which gas clouds are causing the slowdowns. It might even uncover new pulsars or magnetars hidden in the noise, turning their steady pulses into probes of the halo's invisible structure. Perhaps most intriguing are the missions designed to study dark matter directly, like the European Space Agency's Euclid telescope. While not exclusively focused on Andromeda, Euclid's detailed maps of galactic halos across the universe will test whether the strange dark matter clumps we've detected in Andromeda are universal quirks or local anomalies. If they appear elsewhere, it could revolutionize our understanding of how dark matter shapes galaxies from the shadows. These telescopes won't work in isolation. They'll form a network, each instrument filling gaps the others can't reach. Webb's infrared eyes will spot cool, ancient objects. Roman will chart their distribution. The ELT will scrutinize their chemistry and motion. The SKA will trace their magnetic fields, and Euclid will connect it all to the dark matter puzzle. Together, they'll transform the halo from a graveyard of curiosities into a living laboratory where we can watch galactic evolution unfold in real time. The questions these tools might answer are as exciting as those they'll inevitably raise. Could they find evidence of primordial black holes hiding in the halo, detect the gravitational waves from merging neutron star pairs, or even uncover entirely new classes of objects we haven't yet imagined? Whatever they reveal, one thing is certain: the next decade will rewrite Andromeda's story, proving that even our closest galactic neighbor still has secrets left to surrender. From the ghostly hydrogen cloud spinning defiantly against Andromeda's rotation to the crystalline white dwarf diamond glittering in the dark, each of these 30 strange objects tells a story of cosmic chaos and creation. We've wandered through stellar streams, shredded remains of devoured dwarf galaxies, and witnessed hypervelocity stars racing toward intergalactic exile. We've puzzled over pulsars with hiccuping signals and X-ray beacons with no visible source. We've stared into the great Andromeda void, a sphere of nothingness that defies explanation, and traced the faint glow of phantom galaxies that might not even exist. Every corner of this halo holds something unexpected: neutron stars locked in gravitational dances, rogue planets adrift in the void, and magnetic scaffolds weaving invisible order into the chaos. Andromeda's halo isn't just a graveyard of galactic collisions, it's a living, breathing frontier. The same forces that forged these oddities are still at work today, reshaping the halo with every passing eon. Dark matter tugs at stars we can see, revealing masses we can't. Gas clouds collide in slow motion, setting the stage for future stellar births. even now, something new might be creeping into view. A dormant black hole, a swarm of primordial comets, or perhaps an object so strange we lack the language to describe it. The wonder isn't just in what we've found, it's in what we haven't. For every bizarre artifact catalogued, there are countless others lurking just beyond our telescope's reach, waiting for the next leap in technology or a stroke of observational luck to unveil them. This is the magic of astronomy. The universe is always one step ahead, hiding its grandest surprises in the shadows. Andromeda's halo reminds us that galaxies aren't static paintings but violent, evolving masterpieces where even the quietest corners hum with unseen activity. So keep looking up and wondering, because the next cosmic revelation might be hiding in plain sight, just waiting for a curious mind to connect the dots. If unraveling mysteries like these excites you, don't miss our deep dives into the cosmos. Hit subscribe and join us as we explore more of the universe's greatest enigmas, one bizarre object at a time. The universe is stranger than we imagine, and the next discovery could be just one video away.